All right, well, welcome. My name's Jesse Mason. I'm going to be giving you our tour of the solar system. I think we'll start out with a song. You guys know the tune of the song, but I'm going to teach you a song. It's going to help us get through the planets. Of course, you've seen planets up here. The song goes, Mercury, Venus, Earth, and Mars. The first four planets are little and hard, and you'll find out why in a moment. Jupiter's big, Saturn has rings, Uranus is turned, and this is quite a mystery. Oh, Neptune's the last gas giant world. Round our sun these planets twirl. You guys got it? All right, one more time. Join in if you got it. Mercury, Venus, Earth, and Mars. The first four planets are little and hard. Jupiter's big, Saturn has rings. Uranus is turned, and this is quite a mystery. We'll talk about that. And Neptune's the last gas giant world. Round our sun these planets twirl. What about the one on the end?
Yeah.
That's not a planet anymore.
What?
And we'll talk about that too in just a bit. So, our tour of the solar system starts with Sol, which is the name we give our star. We know now that the stars in the sky are similar to our sun in many ways, and this is ours. It's actually a pretty, I don't want to say boring, it's very active, but it's a pretty ho-hum star in terms of size. A yellow or orange dwarf. Of course, we say it's a dwarf, but it's massive compared to our planet, which is going to be dropping in on the right. There's Earth. That's our planet compared to the sun. 1 million of our planets can fit inside of that star. It's enormous. What you see coming off of the edge of the sun there next to our planet is called a prominence. If it bursts off and makes its way out from the star, they call them a solar flare. Sometimes they impact Earth and cause disturbances. But we see those from time to time. Our sun, I said, is active, and this is a measurement, or at least a qualitative measurement of its activity. These are what? Does anybody know what these are on the left?
Sunspots.
They're sunspots. They're sunspots. And what sunspots are, if we had made it out earlier in the day with the solar telescope, we could have seen one. A sunspot is really just a cold spot, and I'm putting cold in quotation marks because they're still very hot. They're just cold compared to the rest of the surface of the sun, so they look a little darker. Those sunspots are sort of a proxy for the activity on the sun, and typically when you see sunspots, it means there could be solar activity, and we use sunspots to predict whether or not there will be any solar activity headed our way. Our sun goes through these approximately 11-year cycles, where it will be very active, have lots of sunspots, and then it will be very quiet and have no sunspots for months, maybe even a year or two at a time. Right now, we're headed towards a minima, but so there's one sunspot up there right now.
So why do sunspots affect the atmosphere, things called radio waves?
Sunspots can lead to solar flares. And solar flares can head our way, and when they head our way, they can interact with our magnetic field, and some of that activity can inadvertently affect our electronics. In some cases, it can even have devastating consequences. Like a century ago, there was a very large solar flare that struck Earth, and it even interacted with our power lines. It's called the Carrington Event, if you want to Google it. Currently, scientists, both engineers with the power grid and astronomer scientists, they are working towards possible solutions towards a second Carrington Event. We kind of feel like it's inevitable to happen, but we don't know how often these things happen. Clearly, it's not every other year. It's more like every century or couple.
What's it spelled? How does it spell? What is
Carrington,
it?
Carring, T-O-N, Carrington. Yeah. So that's those are sunspots. This is not a sunspot, though it looks like a spot. This is what it looks like when a planet, not ours, gets in front of the sun. This is Mercury, I believe. No, I'm sorry, this is Venus. I took this picture back in, I think, 2012 when we had what we call a solar transit of Venus. Venus crossed the disk of the sun, and I projected it from that red telescope you see down here. I actually brought this telescope tonight, so we'll see some, I think we're going to use it to look at the moon. We can project an image of the sun on here to safely view it. And so that's an image of Mercury, I'm sorry, again, Venus, crossing the disk of the sun. And this is, anybody? This is
Mercury?
not the moon.
Mercury.
This is the moon. That, on the left, is Mercury. And it does exhibit phases like our moon. And I put it up there to fool you guys, to show you that Mercury looks very similar to our moon. It has craters. It has that grayish surface area. The similarities to the moon stop, though, right there. Mercury has a magnetic field. I guess it doesn't have an atmosphere, though, much like the moon. Show you some more images of the craters.
Do all the solid planets have magnetic fields?
No. I believe Mars's magnetic field is no longer active. But we think it had a magnetic field at one point in time. The magnetic field is derived from a molten interior, and we believe Mars, its molten interior, solidified. This is an image of Mercury's surface. This is a 100-mile-long cliff. They call it a scarp. We believe this formed when the planet was contracting during its formation. Did I say this is 2 miles high? It's a 2-mile-high cliff. I have a friend that's a rock climber that would love to go there and climb it. There are many places in the solar system he'd like to venture and have his way. After Mercury, we have this is Venus. This is Venus. Mercury, Venus, Earth, and Mars. This is Venus in ultraviolet. I'm going to show you it in several wavelengths. I wanted to include this one because it's in its crescent phase. Venus exhibits phases just like our moon, and even through a modest telescope, so some say you can even see it with binoculars, you're able to pick up these phases. It is the phases of Venus, along with a couple other things in our solar system, that led Galileo to conclude that the planets do, as Copernicus had suggested, move around our sun and not around the Earth. This is an optical, meaning this is the visible light we see from Venus. If you could travel there, this is what you would see with your own eyes. This is why I call Venus the windy planet. I'm sorry, the cloudy planet. Not clouds like ours, though. And if we blow away the clouds, we can see the surface of Venus. This is a radar image of Venus. So we're peering through the clouds with radar, seeing the surface of the planet. You can kind of see the textures on there. Occasionally on these images, you'll see stuff like this. And you wonder, what the heck is that? What's going on there is it's an incomplete data set for the planet. Of course, what you're seeing is actually a composite of all these different images. Just so happened that the bottom portion of the planet didn't get imaged along with the rest of it. And I throw this up there to remind you guys where we got the names. This is, does anybody know what this is? This is what everybody calls Venus de Milo. It's actually Aphrodite de Milo. It's a Greek statue, so it was their Greek goddess of love, Aphrodite, which the Romans renamed to Venus. Some radar imagery from the planet. You can see some elevation information. It's not perfectly flat. And it has several of these. This is a radar image of a crater. So all the interior planets have these craters on them. This is an interesting one because it has this lava flow pattern around it. This is a rill pattern. This graph paper terrain, they call it, is on the surface of Venus. We're not sure if it is, I believe it's a geological contraction, much like that scarp we saw on Mercury. But the spacing of these are on the order of 1 kilometer. So very large features. And we know that Venus was geologically active. We see plenty of volcanic activity, and this is what we call a rill. This used to be a tube filled with lava, and it collapsed. We see these on planets that have volcanoes and volcanic activity. I believe we have some on Earth. Definitely see some on Mars. Two craters here. Ejecta pattern coming out from it.
Are these impact craters or are these volcanic?
This is an impact crater. And this is not a crater. This is an extinct volcano. And what you're
The Rorschach test.
Some of them look like that. This is a volcanic flow pattern coming from this extinct crater. This is one of my favorite craters on Venus. One of my favorite volcanoes. They call it the tick volcano for obvious reasons. What's unusual about this is that the summit of this is concave rather than convex, which is a little bit unusual for this type of volcano. There are even more interesting volcanic activity on the planet, and that's these pancake domes. These pancake domes, I don't believe we know exactly why they formed. They're about 20 kilometers in diameter. And if we combine this with some radar data, we can see, and they colored it to look like lava because it was a lava at one point in time. We can see it from the side. So these are what the pancake domes look like here on Venus. They did the same radar trick here in this next image where we have, it's a mountain. It's a mountain. We didn't actually have a probe flying sideways. We just took information from the radar and combined it to synthesize this image. We do happen to know what Venus looks like on the surface because we've been there. In 1982, after several failed missions, the Soviet Venera mission, number 13, I believe it was, landed on Venus and survived 127 minutes, which is a long time to survive in a pressure of 90 Earth atmospheres and at temperatures of 850 degrees Fahrenheit.
Now, were those the actual pictures, or was that just a coloring?
This is an actual image. This is an actual image. And what you're seeing here is the lander's, feet or base portion. This is the lens cap that was designed to pop off upon impact. So the camera's lens popped off and they took these pictures. And actually, I have an image of it touched up color-wise, combined with some other images from the surface. This was recently put out by a gentleman named Don Mitchell. He analyzed the pictures and was somehow able to tease out what the quote-unquote real color of the surface of Venus is. So this is what it looks like. If you could land on Venus and walk around, of course you'd need some crazy spacesuit to do so. Something more like a diving helmet. A desolate place. And where are we next? Is that Mars? Does that look familiar to anybody? This is our own moon. As we move out from the center of the solar system, the outer solar system, this is the first moon we come to. That's not the last one. We'll see several of these. This is our moon. This is Earth's moon. Why does it look red? The sun is definitely shining on it, but it's not giving it its full light. Something got in the way. The Earth. The Earth got in the way. So what happens is once in a while, as the moon is making its way around the planet, things line up just right for our planet to get in the way of the moon. And it covers the moon nearly perfectly, and light that passes just around the edges of Earth, in fact, as it's passing around the Earth, it actually goes through our atmosphere. And when it does so, it throws off the blue color. That's why our skies are blue, because it scatters blue. And the remaining light strikes the moon. And what's left when you take blue away from white light? You get reddish light. And so lunar eclipses are red. What are solar eclipses? What color are solar eclipses?
Gold.
What are they?
Gold.
Goldish? They're kind of black. I guess it depends on the type of lunar or solar eclipse. When the moon gets in front of the sun and it's spaced just right, you'll see what they call a total solar eclipse. And when that does happen, the blue sky turns transparent just like it is at night, and you can see the stars. And I bring this up because we have one coming up this next summer. I highly recommend taking advantage of it because the total solar eclipse is happening in our soil. It's going from Oregon to North Carolina on August 21st. August 21st this coming year.
You have a lunar eclipse. About how long does it take for your shadow to totally cover the moon?
I want to say 20 minutes of what they call totality, where it's like this, where it's red. But after about 15 or 20 minutes, then it starts to bleed off, and it shows sort of like the same kind of phases in a way as it does when it's actually going through the phases that it does. But the whole lunar eclipse lasts, I want to say, on the order of 2 hours. A total solar eclipse lasts about 4 to 6 minutes. But they are memorable minutes because you go from daylight to nighttime in seconds. And it's an otherworldly experience. So August 21st, mark your calendars. Of course, this is the image of the moon that we know about, that we know and love. This is how you see it when it's full. You have an enormous crater here. This crater, Copernicus, sent ejecta when it happened. This happened many millions of years ago, perhaps even billions of years ago. Throwing ejecta as far as 1,000 miles across the surface of the moon. Enormous distance. And I don't remember if we'll see this tonight. Let me think about it. I think we'll be able to see Copernicus tonight. Unfortunately, you don't really get to see those ejecta patterns unless it's a full moon. You guys would be treated to something even more incredible. When you see the terminator, the line between light and dark, you'll be able to see relief, which means you'll be able to see the craters better. But if you do get a chance, grab a pair of binoculars when there's a full moon out and take a gander, and sure enough, you'll see giant Copernicus. This is the Copernicus crater, and this is a real image taken by a lunar orbiter in the 60s. They were scouting sites to land. What you're looking at is a 4-kilometer deep crater. You can see the what they call the rebound terrain in the center of that crater.
What's the mass of the moon compared to the Earth?
That's a good question. I was going to say, if I would ballpark it, I'd say like 2%, 3%. This is a good time to actually get out a demonstration. I brought a bunch of, I'm not a sports guy. I mean, I love playing them, but I just don't have any time to follow anything. But I do know that this is a basketball and that this is a tennis ball. And could I get your help for a second? This is roughly the size comparison between the Earth
1/8.
and the Moon. What's that?
Like the 1/8. I don't
I'm not entirely sure, but because the density is a little different as well. Anyways, this is the size of the moon versus the size of our planet, and it always surprises people. It definitely surprised me the first time I figured this out. The distance between the two. Because I kind of, yeah, go ahead. Hey, walk over there. I always thought it was like, I actually thought it was like here-ish, right? But the distance to the moon is like 250,000 miles. And in this scale, it would work out to be something more like, I mean, it looks like it's right there above you, right? When you're looking at it, but it's actually more like, about here. About here. Basketball and tennis ball, it's about 25 feet, 24 feet separation. It's an immense distance. It takes light, thank you. It takes light about a second to traverse that distance, an immense distance. The distance between the sun and Earth, that's 93 million miles, so it takes light about 8 minutes to get here. So when you see light coming from the moon, like off these craters, this is called a crater chain, by the way. Some kind of meteor was broken up, torn apart by gravity, and splayed across the surface. When you see this moonlight, it's taken a second for the light to get here from that moon, but to get from the sun to the moon, it takes about 8 minutes. Same thing for our planet. So that light's about 8 minutes old. An immense distance. This is an image, of course, very famous image called Earthrise. This was taken by one of the poor astronauts. He got to go all the way to the moon, but he didn't get to land. He got to orbit the moon. This was an image taken by an orbit. As they were orbiting around the moon, they caught this image of the sun coming up over the horizon. They call this, I'm sorry, not the sun, the Earth. They call this Earthrise. What's interesting, I find, is that if you lived on the moon right here, you would never watch the Earthrise. Why not? The answer is right here. We always see the same face, don't we? We always see the same face of the moon. Until we sent an orbiter around the backside of the moon, we didn't know what was on the other side of the moon. We always see the same face. I say the same face. Do you guys actually see a face? Some people can see it. I always struggle to see it.
You ever been to Traverse City?
Yes.
That one path that they have where they have the planets?
No. Oh, a planet walk. Yes, I was thinking about taking you guys for a walk tonight, but...
That's really cool because as you go down that path, the planets are laid out supposedly in the representation of the distances.
And the sizes, yes.
Yeah,
the solar system walks are very popular. I would have loved to do one tonight, but they're a little bit restrictive as far as time goes. You need to be, first of all, you need to have your walking shoes because it's a long walk. Yep. And second of all, you need the extra time to do so. But here's the face on the moon, or so I'm told. You've got an eye, a nose, and a mouth. That's, yeah. Is that? Or is it eye, nose, mouth? I don't know. I'll tell you what. As I got into this, I started learning about other cultures, what they see on the moon. And I find that I see nearly every time now the rabbit, which is an Asian tradition. The rabbit on the moon, you got the ears and the body, and he's like cooking something in a pot. I think that's something that's like a tradition. But I always see the ears. Or another old European tradition is instead of ears, those are legs. There's the body. And the guy's carrying something on his shoulders, maybe like, I don't know, wheat. Or Shakespeare even used this, a pole with a lantern on it, a lantern man on the moon. Anyways, So we always see the same face in the moon. I guess we can disagree on what face we see, but we always see the same face of the moon because it's tidally locked to our planet. Meaning to say that the gravitational dance we've taken puts us in such a way that the moon is always showing its same face. But the upshot of that is if you did buy property on the moon down here, Earth would always be here. It might move a little bit back and forth, but you pretty much see Earth in the same spot of the sky all the time. Name that astronaut, anybody? Not Buzz, not Neil. Can you name any other lunar astronauts? No, this is not from the first. This is Gene Cernan, yeah. He was the last guy on the moon. Everybody remembers the first guy. He's the last guy on the moon.
Did he actually go twice?
I don't know that. I'm not sure. I didn't know any astronaut went twice. Should be so lucky. This is some junk we left up there. Of course, a really useful piece of junk. This was the second rover. Amazing technology. If you ever get a chance to YouTube these guys driving it around, they had a hoot. Also fun to YouTube them walking around the moon talking about what it's like. He's next to a big boulder. I think he's collecting rocks. There's the LRV over there. This is an image relatively recently. This is back in 2009. We took a spacecraft, flew it to the moon, and then we smashed it into the moon, or at least smashed part of it into the moon, with the intent on measuring the plume that came up from the impact. And when we did, we found water, which is really incredible because we suspected it, but we weren't sure, and we finally got confirmation. There is water on the moon. It's not liquid, it's an ice form, but it's there.
Is water common?
It is. It is common, but issues with the formation of the solar system prevent all planets from enjoying that commonality.
More ice.
For example, we'll get to Mars, but Mars had more water than it does now, and there's some ideas why. Yeah, a lot of it's in ice form. Most of it's in ice form. I said we see the same face on the moon. That's a white lie. We get to see a little bit more than half of the moon. We see about 59% of the moon. It does this thing we call a nutation, where it kind of bobs and weaves. It has to do with how the moon does not orbit Earth in a perfect circle. It's elliptical. And at different points on that path, we get to get a peek on the limbs of the moon. We get to see different parts of it. That's why I said Earth kind of bobs and weaves a little bit in their sky. So that's the moon.
Is the other side of the moon kind of cratered as much as the side we see?
In fact, I believe it's more heavily cratered. Yeah, it took more of a brunt during what they call the late heavy bombardment period, billions of years ago.
Want to mention briefly how the moon was formed?
There are different theories. But the best theory, I'll bring the moon back up. The best theory we have is a Mars-sized planet that they've dubbed Gaia, I believe. Smashed into Earth billions of years ago, about 4.5 billion years ago. And as those two planets collided, there was debris from the collision that was thrown off into orbit. And much of that debris settled on the planet, but some of that debris, what is it, roughly an eighth or something, coalesced into the moon. That is, I think they call the giant impact theory, or giant collision theory of the formation of the moon. That's nearly universally accepted now.
So why does matter always clump into balls?
Gravity. Mass wants to be with other mass. And why does it do that? You have to ask Einstein. It has to do with how matter, mass, and energy bend space and time. So here's the rusty planet. I call it the rusty planet. And the reason is its color. And why is it this color? It's because it's rusty. It's literally rusty. Iron oxide on the surface has oxidized, and we have the rusty color. It literally rusted. Gorgeous planet. I think we'll be able to see this tonight so long as the clouds subside.
Is it oxygen for rusting? Oxidation,
There is oxygen in the atmosphere, but not nearly as much as there is here. It has a very weak atmosphere, something like a tenth, I want to say, of the atmosphere that we have, that we enjoy. These are the two moons of Mars, Phobos and Deimos. They're very tiny moons. They go around Mars pretty quick. And this is the North Pole at Mars. Really interesting spiral pattern here. That's due to something they call katabatic winds. The cool air near the surface of Mars, as it rolls off, because the planet's turning, experiences the Coriolis effect. And it kind of gives you that motion of not only outward, but pushed that way. So you got a gorgeous spiral polar cap. And this feature here is called Chasma Boreal. This is a side view of that chasma. Actually, I have a really recent image from that spot, from above, from the Mars, what is this? The High-Rise. I think they call it the High-Rise probe. We've got, it's basically an avalanche. This is about almost a kilometer tall cliff, and debris coming from the cliff falling onto the surface, shooting out about 190 meters, 200 meters, catching an avalanche. So there's still stuff going on Mars. There's really interesting stuff going on Mars. And of course, we have been there. We are there. This is an image from Mars.
Is that white stuff water crystals? Water?
Nope. This is an awful transmission. This was, I think, the first transmission from Mars. This is after 11 years of failed missions. This is the Soviet, I think they called it Soviet lander, Soviet Mars lander. First image, almost completely worthless.
The previous slide also showed something white. What was that?
This down here? Yeah, that's most likely that's solid water. That's ice.
Oh, so, I mean, so it's no longer a secret. Mars has water.
Oh yes, and I'll say more about that in a moment. Yes,
Okay.
we've been there. We've played with it.
Okay.
So this is the first transmission from Mars. Not exciting. This is from our first mission to Mars, Viking 1. This is actually the first image from Viking 1. I'm sorry, this is Viking 2. This is back in, I think, 76. Another image, I think that might be Viking 1. Of course, the image that they've been hiding from us.
I knew it.
How close these colors are to the red ones?
The real ones, this one's pretty darn close. Somewhere between those two. I'll tell you where it's closest, right there. That nails it. This is actually the Curiosity rover doing a selfie on Mars with that's the sun through the atmosphere there. They somehow cropped out the arm that's holding the camera from which he's taking the picture. But that's what the surface looks like. Very real.
That's the rover?
That's the rover, yep.
So the arm is out this way.
Yeah. And somehow they cropped it out. Maybe they took several images and just took it out. Mars selfie. So I said we've been there, we've played in the dirt. There it is. There is the scoop that looks like it's off my Tonka truck, but that's from the Phoenix lander. And it scooped the surface, and guess what it found? Solid water. Vanilla ice cream. Solid water. This is in 2008. Mars has water. Since then, we've actually witnessed liquid water on Mars. So Mars experiences seasons just like Earth because of its axial tilt. That is to say, the planet, as it spins, is actually kind of spinning with a tilt to it. And when its north pole is leaning towards the sun in the orbit, its northern hemisphere is experiencing summer, and when its south pole is facing away, it's experiencing winter. And what we have here is, during a Martian summer, a melt. This is liquid water. Well, they call it briny water because it's very salty, but melting in this cliff.
Is it built in about 7 hours?
You know what? I don't know. I don't have the number offhand, but I do know it's in the slide towards the end of the slideshow. We'll see it. So after all this, we start to suspect, and this is not confirmed, but we suspect that Mars had much more water in its distant past, and that it lost it to evaporation and its inability to protect itself from the sun. I said that we have an active magnetic field, and that does, for the most part, prevent us from experiencing the brunt of those solar flares. Mars does not. It's no longer magnetically active. Additionally, Mars is smaller, so it can't hold on, because of the phenomenon of gravity, it can't hold on as well to its atmosphere. So as it lost its atmosphere, so did it lose its water. This is artist representation, what they suspect that Mars may have looked like with a liquid water surface. Mars has craters. This is one of the famous craters called the Galilean Crater. It looks like a smiley face. Give you an idea of size, the elevation of the rim here is something like 2 miles. It'd be great to go climbing on that if you liked that kind of thing. And there's Mars. This is a statue from Rome. The Greek counterpart, does anybody know? The Greek counterpart for the Roman god Mars? Ares. Ares. God of war. War! Look at that. That is an incredibly large canyon. On this, it looks like it was slashed there. Much larger than our Grand Canyon. It makes our Grand Canyon look tiny. There it is against the map of our country. This is the canyon they call Val Valles Marineris. It's about 100 times the size of our Grand Canyon. This is what it looks like from above. Zoomed in on a side so we could see what they call landslide debris from avalanches.
So the top is the top of the picture, and this is what?
So this is upper elevation, and this is the rim. This is part of the rim of the Valles Marineris. This is, we suspect, relatively recently, because it hasn't really eroded away much. It's still kind of, these gullies are still just sitting there.
That's all water?
No, not water at all, just wind.
But is it water that makes that?
No, there's no, the idea of liquid rivers running, we don't believe that has happened even in the last million years. It's been a long time since it had liquid water on the surface. Probably on the order of billions of years.
But I thought Lowell said that they had canals all over it.
There are canals, and I think those canals are geologic features, not aquatic features. So from volcanic activity. And speaking of volcanoes, here is a supervolcano. This is the largest, what they call shield volcano. It's a type of volcano. It's the largest type of volcano, and this is the largest one in the solar system. This is called Olympus Mons. Mount Olympus, essentially. Elevation of 22 kilometers. It towers over our volcanoes. This is a side view. I think this is a radar image. To give you an idea, the top of that volcano reaches up to the top of its atmosphere. It's basically peeking out into space, it's so large.
No
I'm sorry?
Don't want to get a cone.
No, it's not a cone volcano. You got, what is it, cone volcanoes. Should know this, I just took a geology class from a friend. There's cone and shield, I can't remember the intermediate one, but the cones are typically the smallest.
So it's much taller than Mount Everest.
Yes. Yes. It's not the tallest mountain in the solar system. We'll get to that, and it's a surprising location. But Mount Everest is what, like 5 miles? This, they call it escarpment. That cliff there is 4 miles. So Everest would just be peaking above that part of the volcano. Enormous. And these are dust devils from the surface of Mars. Mars is famous for its dust storms. Here's an image of a dust storm making its way across the surface of the planet. And if you've seen any Hollywood movies about astronomy lately, you might recognize this gentleman who got stranded because of a so-called dust storm. That's Matt Damon in the movie The Martian. If you haven't seen it, highly recommend it. Outstanding movie. And one of the most impressive aspects of that movie is the landscape filmography. They nailed it. They nailed it. That's really what Mars looks like. And nearly all of the science in the movie is accurate. Dust storms so large that they encompass the entire planet.
Did they do this film in Nevada? Where did they do the film?
I don't know. I don't know. I bet they did it on a blue screen, or a green screen, rather.
Did our spacecraft encounter one of these?
Our spacecraft, our landing craft have survived them, for the most part.
They were in the middle of this.
Oh, was there a spacecraft during this? Oh, yes, yes. Yep, we knew about the dust storms before we went. The dust storms that, encircle the entire planet, you got to remember that the atmosphere is only 1/10 of ours. So, a beating dust storm on Mars is like a light breeze here. So, not a very dangerous thing to be around. Still, look what it does to the image of Mars. You can't even see through it.
So it must be losing dust particles too in the space.
Not much. No, the dust is heavy enough for the gravity to maintain its grasp on it. It's lighter elements that the planet has trouble holding on to. So let's see, Mercury, Venus, Earth, and Mars. The first 4 planets are little and hard. Next up is Jupiter. Almost. We forgot an important stop on the journey. This is an asteroid. This is the king of asteroids, or I would say the king of dwarf planets. Really, it's the largest asteroid in the solar system. We've been there. It's comprises roughly 1/3 of the mass of the entire asteroid belt. This is Ceres. This one asteroid, yes. Yep.
Is it spherical or just a...
Yeah, it is spherical. Yep.
That's unusual, isn't it? Usually they're not spherical.
Well, it's a very large asteroid. And you can see a little mountain here. I say little, but it's actually 4 miles high on this tiny asteroid. So that's Ceres. We got there, I think, 2 years ago. Took some pictures. This is a different asteroid. This is Vesta. If Ceres is the king, this would be the prince. It's the second most massive asteroid in the system.
Which one did we land?
I don't think we've landed on an asteroid. We've just taken pictures of them. We landed on a comet, which is actually more impressive, I believe. Asteroids roughly transit they move around the sun in a roughly circular path, whereas comets come in this very skinny elliptical path. So that's Vesta. Vesta gets the award for tallest mountain in the solar system. This is the Rheasilvia Crater, and this mountain, this rebound aspect of the crater, that rebound peak, is 14 miles high from the base. Enormous. And for a asteroid that's only 300 miles wide, that's an incredible size.
How many miles?
It's 300 miles wide.
The base.
No, I'm sorry. No, that's the size of the crater.
Oh, great.
Yeah. I think the diameter of the asteroid is maybe 350. If we go back, can we see it? I think it might be on the other side of the image. Yeah, it's on the other side. Rheasilvia. This is a famous asteroid because this is the asteroid Ida, 243 Ida, and this is its tiny moon. Of course, we don't get to call it a moon because the asteroid's not a planet. We only give that designation to planets. So it's a satellite. It's kind of like a moonlet. And it orbits the asteroid as the two of them go around our solar system.
The previous satellite, was it actually rotating around its own axis? Or was it just the camera doing that?
I believe it was.
Well, it has a rotating.
I believe so, yeah.
It's rotating.
Yeah. If you get a chance to go out to the asteroid belt, this is not what you would see. Thanks to George Lucas and his cohorts at Star Wars, this is what everybody sees when they think of the asteroid belt, but this is not what you would see. The asteroid belt is immensely large, and though there are about 150 million asteroids in the belt, if, let's say, you were in the vicinity of this asteroid here, you probably wouldn't see any other asteroids in the field of view. If you did, it might be a speck over here and a speck over there, but the idea of having to dodge the asteroids with your spacecraft is, it makes for a good movie, but it's not how it is. Asteroid belt is very sparse.
That means the Imperial cruiser could catch him.
Yes, yes. Or you'd have to be a very talented hider. So this is an image of the asteroid belt. This is an interesting image because it shows you the main asteroid belt, which is here between Mars and Jupiter. But it also highlights 2 or 3, depending on how you want to define it, different kinds of asteroids. There's the main asteroid belt, and then there's the Hilda asteroids, which have an actual triangular shape. And the reason it does is because of these asteroids, which hide in a location in Jupiter's orbit that is called a Lagrange point. A Lagrange point is a point at which you experience no net force due to the nearby body. So as Jupiter makes its way around the sun, so do these asteroids. And they get to hide in these 2 spots, these 2 Lagrange points. And because they're hiding, they termed them Trojan asteroids. And I don't know why they decided to label the ones in front of the orbit as Greeks, but all of these are Trojan asteroids hiding in the Lagrange points. And we just detected a Trojan asteroid in Earth's orbit. Of course, you don't have to worry about them jumping out and smashing into us because they're just floating around in those Lagrange points, and they will continue to do so until they're disturbed by some other body. But
so distance between them and Jupiter remains constant?
Yes.
Jupiter moves.
Yep.
Oh, they also move. Right?
Yeah, maybe these Trojan asteroids kind of wobble around a little bit around that Lagrange point, but for the most part, they stay put. Whereas these asteroids move in a circle, these move in each individual Hilda asteroid moves in an ellipse, but the shape of the Hilda asteroid belt is actually triangular. It's a very stable system. And that's seeing these Trojan asteroids in the Jupiter, hiding in the Jupiter Lagrange point, was what tipped us off that we might have a couple in ours, and we finally detected one recently. So this is scary to look at. There are a lot of asteroids. There's like 150 million here, 1,000 or so here, a couple thousand here. Most of them are right there. It looks scary because there's Earth. It looks like it's going to be pummeled soon. This is an even scarier image. This is what we call the near-Earth object path. I call it the Doomsday Spirograph. These are the objects that are currently being tracked by NASA. These are potentially hazardous asteroids, and there are about 1,400 of these zooming around our inner solar system. Fortunately, none of these bodies, and we're looking at bodies that are 150 meters or so, none of those bodies pose any danger to us, but we are monitoring all of them right now, and we're trying to get better at monitoring all potentially hazardous asteroids.
Where's the Earth map?
Earth would be right here. It's the bright, right in the middle of the death spiral.
Is there a plan in place for any?
No, not really.
Yeah.
We're going to call Bruce Willis and his team, and they're going to save the day. I am sure they're working on plans. They just this past year formed a committee or I think it's an organization tasked with saving us if something comes up. The issue, though, is if something comes up, we have very little warning time. So it would probably be on the order of like a Manhattan Project times 100 if we found something. So.
Are there comets in here, in this picture?
No, these are just potentially hazardous asteroids. And, those asteroids are all doing elliptical orbits as they're going around the sun. Comets would come from over here, way over here, probably out in the high school parking lot.
They're not that dangerous to us.
Some of them are. Some of them could be. But we haven't had one in a long time. And so we arrive at the giant planet. This is the king of the planets. This is one of my favorite images of the planet, showing the great red spot. The great red spot, of course, is a giant what?
So,
It's a giant storm. It's a storm, an enormous storm that's been there for centuries. And we actually recently just started detecting it shrinking a little bit. But it's been a relatively stable storm going on the surface that you can see in even a modest-sized telescope. Its lesser cousin, the large brown oval, also a storm, not as famous. To give you an idea of the dynamics of these storms, I'll show you an image from Voyager 1 as it approached the planet. Voyager 1 spacecraft decades ago videoed this. It's really interesting. You can see what they call the Kelvin-Helmholtz instability, those little wavelets occurring between boundary layers.
What does the storm consist of?
Gases. The whole planet is a gas planet. So we left the rock. I said the first 4 planets are little and hard. They're the rocky planets. When you get out to when you get out to Jupiter and beyond, they're all gas planets. And what's beneath that surface? We don't know. We suspect there's some kind of liquid ocean beneath that gaseous surface, but we're not sure.
What gas?
I don't know. I was going to say my inclination is methane, but I don't remember exactly.
what decide those patterns? What makes it?
What makes the patterns? Two different things. And I'm speculating at this point because this is definitely not my expertise. In fact, my expertise is not even astronomy, but I'm just super into it. You have convective cells, much like you have on our planet. In fact, I want to say like our planet has 3 convective cells, just like you're seeing here. And those convective cells are interplaying with the Coriolis effect because the planet's rotating and the top part is rotating at the same spin rate, but it's slower because it's closer to the poles. And so you get this convection from differing heat, and as it descends, it interacts with the other layers, and you're seeing those 2 boundaries. If I can go back to see it spinning again, you can see those 2 boundaries. This top layer doesn't seem to be moving very fast. This one's a little faster, this one's even faster. And you got counter-cyclic rotation over here.
Is planet tilted on its axis?
I believe so, not extremely. but again, I think we'll get to a slide that has all the numbers for those axial tilts. I include this next image because this is what Galileo saw when he pointed his telescope toward Jupiter. This is what, if we had Jupiter in the sky tonight, we would see. This is one of the most remarkable things to view, because what you're looking at here is Jupiter and 4 of its moons. When Galileo turned his telescope to the heavens, he heard this, heard rumors at the market that this eyeglasses maker had figured out a way to make a spyglass, how to make things look closer than they are. And he thought that was really nifty, so he went home and fashioned his own telescope in one night. And I think his plan was he was going to take it to the market and make money with it, because if you have a telescope, you can see what's coming over the horizon. Of course, he worked in Italy, and during that time they had, Venice was a huge merchant location, and I think he was going to sell it to the merchants so they could spot the ships coming over the horizon, figure out what's on board, and then prepare to sell it in the market. And of course, he decided to turn it to the heavens, and when he did, it was an earth-shaking discovery. Like I said, the phases of Venus was one piece of evidence for not everything goes around the Earth, but this was really the clincher. You can watch these 4 moons go around Jupiter in just a couple nights. It is if you have a couple clear nights and a modest telescope, you can actually watch these moons move. In fact, Io, I think this one's Io, you can actually watch Io move throughout a single evening. It moves so quickly around around Jupiter. So when he saw these moons going around Jupiter, he said, clearly, not everything goes around the Earth, and he got in a lot of trouble for that. But for him, we named the moons the Galilean Moons of Jupiter.
Are they gases or are they solid?
The moons? They're all solid. They are all solid.
What keeps them from not gravity not plopping?
The same thing that keeps our moon in orbit. It's got lateral motion going. So it is falling, literally, it's falling towards Jupiter, but it's moving so fast that it maintains a circular orbit. So this past summer, one of the most exciting things in astronomy occurred. We had a probe that reached Jupiter. It was the Juno Probe. It arrived on the 4th of July. And first thing I can say about it is Juno broke the speed record. It is the fastest man-made object we've ever fashioned. It traveled 12,000 miles per hour, something like that. Give that number a perspective. It's like here to Monroe in 1 second. It is very fast. And after spending, I think it was 5 years in transit, it finally reached Jupiter. And what's exciting about this is that the whole purpose, if you know your, I think it's Roman mythology. If you know your Roman mythology, you'll know that Juno was the goddess that could peer through the clouds of, was it Zeus or Jupiter, the Roman counterpart, peer through the clouds of the god to see his insides, to see what he was made of, his heart. And so Juno, the spacecraft, is actually going to be looking through the clouds of Jupiter and telling us what's beneath. I said we suspected there's a liquid ocean. Juno will tell us. And towards the end of its mission, and I think it's going to last about 2 years there, it will eventually plunge into the surface itself, sending us data as it goes, as long as it survives. So be on the lookout for information from the Juno spacecraft.
Like on the other side, it's on gas.
If we were wrong, that would be really funny. The scientists would freak out. It'd be great.
Wow,
It wouldn't be the first spacecraft that survived longer than we thought it would. Juno took a video as it was approaching Jupiter, much like Voyager did. Here's an image of the Galilean moons moving around Jupiter. I said Jupiter has more moons than these 4, but these are certainly the most famous, and they are some of the most interesting moons in the solar system. We have Io here, Europa, Callisto, and Ganymede. And they comprise 4 of Jupiter's 67 moons. It has 67 moons. It has the most moons in the solar system, just barely edging out Saturn. So Io is interesting. It's a volcanic moon. It is volcanically active. We caught a picture of it spewing some of its stuff into space. In fact, shortly after we got a picture of it, we got a movie of it. And this is Io spitting volcanic material into space. That's an altitude of about 200 miles to give you an idea of how far it goes. In fact, when Jupiter exhibits auroras, and I'll show you a picture of the auroras, we suspect that some of that aurora, some of the material that's causing the aurora actually comes from Io.
It's one thing interesting about that projection is that angle is not shooting straight and then curving. Not at right angles. So it's like,
Well, it's shooting straight up but spraying outward.
oh, it was shooting straight, but it
Mm-hmm. Yep.
this angle of
So a true color image of the surface. This is a shield volcano, much like Olympus Mons, but it's much smaller. But that's about a 200-mile lava flow. And like I said, active. Some of them aren't, but many of them are. There's a mountain that's about 5 miles tall. I think that one's about 7 miles tall. Favorite moon in the solar system, besides our own? Europa. Europa is solid, but we suspect beneath its icy surface, we suspect a liquid ocean. And those suspicions were confirmed recently when we caught, and I don't think I have the image. Let me see here. It's not a very exciting image. These are close-ups of these cracks on the surface. False coloring to pick out some of the mineral contents. The brown and red is contaminants in the ice. Oh, I do have the image. This is not the image. This is actually a crater. You can see the ejecta coming from the crater, much like the other craters we've seen. Here's the imagery. This is not exciting at all to look at. What you're looking at is a sequence of images from the Hubble Space Telescope. And in red are plumes of what we suspect to be liquid water.
from Europa.
Plumes coming from Europa. Plumes of liquid water coming from Europa. And that's about as good as we can get to knowing that there's a subsurface ocean on Europa. Of course, the exciting thing about liquid water in large quantities is what? It could lead to life. As far as we know it, life lies on liquid water. And if there's a subsurface ocean, maybe we'll find bacteria, maybe even other single cellular organisms. Maybe we can go fishing on Europa someday. We don't know. Ice fishing. The other exciting thing about it is if it's spewing this liquid water onto the planet, we don't actually have to go drill through the ice to find out what's going on beneath the surface. We can just collect some water from the surface and analyze that. And in fact, we do have spacecraft that are being designed just for such a mission. And I think in the next decade, we're going to see 1, maybe 2 missions to Europa.
From the spectrum analysis, we established water and not liquid nitrogen.
Correct.
It is water.
Yeah. Yep. So this is the largest moon in the solar system, Ganymede. There's a legend that it was actually observed with the naked eye hundreds of years BC, but very doubtful.
Is the water that they find H2O, or is it some other water like?
Is it like briny water like on Mars?
Yeah.
I believe it's straight H2O. I shouldn't say straight because of course there's going to be minerals in it, but we don't believe it's a briny water like Mars. And I would also say that as they're doing the spectral analysis, they're analyzing the light that's coming from that plume. I remember listening to the conference where they announced this, and they said they still were inconclusive. Because of course what everybody wants to know, are there organic molecules in that plume? That's the big thing. Are there organic molecules? And the scientists were very cagey about that. So they're still working on it. images from Ganymede. Not exactly sure what causes this. Maybe tectonic activity. Maybe tidal heating in the pole of Jupiter. And this is Callisto. Callisto is the most heavily cratered surface in the solar system. And that tells us something about its age, because we believe in the early solar system there was a lot of impacts going on. And if Callisto is exhibiting such a cratered surface, we suspect it's one of the oldest bodies in the solar system. We suspect beneath the surface of Callisto there might be a saltwater ocean, not as exciting as the freshwater ocean on Europa. Then this is a crater, of course. This is the largest crater that has this concentric ring feature in the solar system. Again, that came from the distant, distant past when our solar system was being formed. So here's some of the auroras I told you about that Jupiter exhibits. Again, some of that we believe is due to the volcanic material being thrown off of Io, landing on Jupiter, being channeled in by its magnetic fields.
This is gaseous, right?
Yes.
So it still has magnetic?
Oh, yes. Yes, yes. Jupiter's magnetic field is immense, too.
So you don't need molten iron to have magnetic field?
Well, you need molten something. And I'm not sure. I'm not sure. And, you know, when it comes to guessing what's beneath the surface, I'm not sure we have many clues. My favorite theory is by Arthur C. Clarke, the science fiction writer. He suspects there's a diamond at the center, a solid carbon diamond, the size of our planet. And as we venture further out into the solar system, we see rings. In fact, as soon as you get to the first gas giant, which is Jupiter, you see a ring. This is Jupiter's ring. Jupiter has rings. It's very faint, but it does have them. Not like this guy, though. This is the Lord of the Rings planet. This is, of course, everyone's favorite, Saturn. This is a total solar eclipse picture with the sun behind it. Spacecraft caught it. Spacecraft's Cassini. I think Cassini's going to last another year. Keep sending us images, and then it's going to be done with its mission. Here's a close-up from Cassini of the ring structure on Saturn. Fantastic ring structure. What you're looking at is not, of course, solid rings. You're looking at rings comprised of tiny, tiny rocks. Some of them the size of a grain of sand, up to the size of a house-sized boulder. How does it maintain its ring structure without disturbances? Well, these guys help it. These are tiny moons of Jupiter that go around and shepherd those rings in line. So this one will move forward, this one will move forward, and as it does so, the gravity between the two keep that ring nice and thin. They call these shepherd moons. And these particular moons are called Prometheus and Pandora. A couple of years ago, two years ago or so, Cassini released this image. This is amazing. There are these ice spikes in the rings. Of course, we're looking down onto the rings from above, but what we see here is the shadows coming from these ice spikes. Not exactly sure where these perpendicular structures came from. We suspect maybe they came from some nearby moon disturbing an otherwise flat structure, but these ice spikes are over 1 kilometer tall.
These lines that you see, is it because it's a still picture of a moving object, so typically you see it on blurry?
No. Those are actual divisions in the structures. Yeah, it's not because it's just blurry. In fact, I mean, you look at this, and this is obviously clear. So they look like lines because as you get closer and closer, you'll have divisions in these rings of tiny rocks. So this is an interesting thing on the south pole of Saturn. They have this rotation going on. There's a stable hexagon pattern that as the South Pole rotates, somehow it's able to maintain its shape. They have been working on explaining this for years. They still don't really know how it works. Some kind of standing wave structure, perhaps, similar to standing waves on a membrane. First observed in 1980. Still don't understand it completely. Saturn also exhibits aurorae. This is an image from Voyager 1. Here's an image from Cassini. So the magnetic fields of Saturn as particles are coming in from the sun or from a nearby volcanic moon. I don't believe Saturn has any volcanic moons. Those particles catch the magnetic field. If they're charged, they will spiral inward and strike the planet. And when they do so, just like when they strike our planet's atmosphere, they will excite the atmosphere. And when the atmosphere gets excited electrically, it glows like that, just like a fluorescent light. Beautiful planet. Posing with some of its moon family. Very cool. You can see behind the planet the shadow of the main body on its rings. So I'll show you some of the moons. I'm not going to show you all of them because there are 63 moons of Saturn. I'll give you a sampling. This is Mimas. I call this the Death Star moon because it looks just like the Death Star. Of course, that's due to an impact. That's a giant crater.
What's the name of it?
Mimas. Mimas. This is Tethys. Tethys also has a giant crater on it that kind of makes it look a little bit like a Death Star. Tethys is mostly water ice, some rock. Tethys has a giant canyon going across it. It's one of the longest valleys in the solar system. It's about 2,000 kilometers long, 4 kilometers deep. We think it may be due to a freezing phenomenon on the surface, not entirely sure. More chasms on a different moon. This is Enceladus. I'm showing you moons of Saturn right now. Enceladus is most interesting because, well, okay, until we saw the ice geysers on, or I should say the water geysers on Europa, Enceladus had everybody excited because it had ice geysers. It has over 100 of them. Warm ice erupting into space from cracks in the surface, hurling them thousands of miles into the space. In fact, we believe that one of the rings of Saturn, one of those structure rings, they call it the E-ring, we believe the E-ring may have formed due to Enceladus's ice plumes. And also, interestingly, last year when we flew a spacecraft, we got this, of course, because we flew a spacecraft toward it. When we flew, I think it's Cassini, through this ice plume, they detected organic molecules in the ice plume.
Any theory as to what is pushing that thing up from inside?
I think tectonic activity is the idea, meaning that the Saturn's enormous, right? Not as enormous as the Jupiter. Jupiter is about, we could fit 1,000 of our planets in Jupiter. We could fit about 750 planets of Earths inside of Saturn. So it's an enormous planet. And that planet, when you have a moon close by, experiences a lot of tectonic activity because the far side of the moon experiences a different gravity than the near side. They're similar, but when you have a body like the size of a moon, you're going to have some contraction going on. So basically, the moon's getting squished by the gravity of Saturn, and when it gets squished, it squirts stuff out. That's the leading theory, I believe. More beautiful moons of Saturn. This is Dione. Those wisps are actually cliffs, several hundred meters tall. And again, this is another phenomenon of what we believe is tectonic fracturing. The moon Rhea. It's a big moon, but it's kind of boring. Of course, it's got craters.
Is it a natural color?
Yes. This is a really interesting moon of Saturn. It looks like a sponge. I call it the sponge moon of Saturn. This is Hyperion. It's almost half empty space. What causes that, I'm not sure. I don't think we know for sure. I think our best guess is material has evaporated away into space, leaving behind the holes from where that material came. Maybe it was ice that evaporated into space, not sure. Cool moon though. Almost as cool as this one of my favorite moons in the solar system. This is Titan. If we see Saturn tonight out in the telescope, we will most likely be able to see this moon as well. What's most interesting about this moon? Here's an image of looking through the methane and ethane clouds on the planet. We see lakes and rivers and weather on this moon. Very interesting. Of course, not liquid water lakes. Those are methane lakes. In fact, we can see a subsurface ocean in this image. The sun is reflecting off the surface, and we're able to detect the subsurface ocean. All these are interesting, but not nearly as interesting as this, which is the surface.
Like Mars.
And the reason I can show you this is because we landed a spacecraft on Titan. The Huygens Probe. This is the furthest outpost that our species has in our solar system. So if we get a chance to, no, had long since. In fact, it took several images on the way down, and I believe discontinued service shortly thereafter. But if we do get a chance to look at Saturn tonight and you see Titan, remember that we've got a spacecraft there. This is the tennis ball moon, Iapetus. That dark area we believe is due to sublimation, leaving behind mineral deposits. Iapetus has this crazy ridge going across the equator. It's about 20 kilometers tall, that ridge over the surface. We don't know exactly what it came from. Maybe tectonic activity as it was contracting. Maybe for some reason that part of it stuck out, not sure. So many mysteries in our solar system. And this is a moon that actually we believe didn't form along with the planet. We believe this moon, it's called Phoebe, was captured. We believe Phoebe originated in the Kuiper Belt. The Kuiper Belt is just beyond the orbit of Pluto. In fact, we suspect that Pluto might be a Kuiper Belt object. Large bodies like Phoebe and Pluto migrate into the solar system, drawn inward by gravity's pull, maybe even by the gravitation of Jupiter and Saturn. Phoebe, we believe, got caught by Saturn and has been there ever since. Unlike the other moons, which we believe formed along with the planet, this one got roped in. I said the Kuiper Belt, and I want to show you where the Kuiper Belt is. It's beyond the orbit of Neptune in our solar system. And I believe that the pink ones there are the Trojan asteroids. Orange ones are scattered asteroids, and these are the Kuiper Belt objects. We got an asteroid belt, a Kuiper Belt. Before we get to the Kuiper Belt, though, we have a couple more planets. This is a planet that we discovered after we got telescopes. We didn't know this existed until there were telescopes. It's too dim for us to see without the aid of optics. This is Uranus. And what surprises most people is that it has rings. Like I said, all gas giants have some sort of ring structure, and Uranus is no exception. What makes Uranus interesting is that it's on its side. Most of the planets, as they rotate around the solar system, do so spinning perpendicularly to the orbit, whereas Jupiter orbits on its side.
Uranus.
I'm sorry, yes, thank you, Uranus does. See if I have an image of those axial tilts. This is a close-up of the rings. I believe those are stars in the background that have drifted when they were taking a long exposure. It's from the spacecraft Voyager 2. Some false coloring to show you temperature differences. And this is the slide that I kept talking about. So Jupiter has a 3-degree axial tilt. We on Earth have 23. Mars is 25. So Mars is really similar. so it experiences seasons much like we do. Saturn is on its side quite a bit. Uranus is
Yeah, 90.
turned, and this is quite a mystery, just like the song says. Uranus is turned on its side. We're not sure why Uranus is going around the Earth, or going around the Sun that way. What would your best guess be?
Pushed by some asteroid.
That's our best guess too. Astronomy's best guess is it got whacked really hard by something, and it turned it sideways. But we have almost no evidence to support that beyond it just makes sense. So until we really get more data on that, we don't know. It's a mystery, and exciting mystery though. Almost as exciting as Venus, which you can't really tell in the image, is actually spinning the other way. All of these objects are spinning counterclockwise as viewed from above. Venus is spinning clockwise as viewed from above. As it goes around the Sun, it's spinning the opposite way as the rest of the planets.
That's the only one?
That's the only one. Why it does that? Not sure. Maybe it got whacked. Maybe when it was forming, it had a collision much like we had with Gaia, and instead of making a moon, it just spun the planet the other way. So some moons of Uranus. This is Titania. We believe there might be a liquid layer at the boundary between its core and mantle. This is the moon Oberon, very similar to the other moon. In fact, we suspect liquid between the core and mantle boundary. This is the moon Miranda. Interesting because I call this the cliff moon. Verona Rupes right here, this cliff right here, is the tallest cliff in the solar system at 3 miles. It's nearly a vertical drop 3 miles down from that cliff.
It's like there's a face in there too. See those eyes on the right side?
Trying to see it.
Those 2 eyes. And the nose.
Oh, eyes and nose. I like it. The face of Miranda. Okay, onwards and outwards. We get to the windy planet. And if we could see this through a telescope, all we will see, I might try to get it tonight if we have time, all we'll see is a blue dot. But this is the most distant object in our solar system, the most distant planet. And I call it the windy planet because it has the strongest winds in the entire solar system, clocked at about 400 miles per hour. Very fast. So on this gas giant, you have, of course, different layers of gas. And what you're seeing here is methane clouds riding across a different layer of gas. I think we suspect the deck is made of ammonia and hydrogen and helium. But it has clouds too. This is one of the moons of Neptune. This is called Triton. That surface you see there is not a digital artifact from the imaging. It is what they call the cantaloupe terrain. They have no idea how that cantaloupe terrain got that way. It's the only cantaloupe terrain that we see in the entire solar system. This is another image of Triton. Dark spots are leftovers from geyser eruptions, we believe.
These moons are also gaseous, or is that solid?
I think this moon, we believe, has some kind of subsurface liquid. I shouldn't say liquid. I think we suspect that it has lava. I take that back. No, I think we believe that there's a liquid beneath, but this one actually spews out ice. We don't have any images of it, but we believe that, I said these are leftover from geyser eruptions. What we've teased out from images and data is that those geysers were made of solid ice.
That when the liquid water freezes, it does create.
I don't think it. I should qualify that. I don't think we believe it's liquid water. It's a different kind of. I think it's a different kind of solid. So that's Triton. So we've seen Neptune and the moons of Neptune. We get to, this is actually a Hubble image of this planet. I call it planet in quotation marks because it got fired. This is Pluto. There is Pluto from the New Horizons mission. Arrived last year in July. One of the most spectacular missions as far as uncovering. We were sort of expecting a dull planet, but man, were we wrong. This is a true color image here. The next image I'm going to show you is as if we flew by the planet in a spacecraft and looked backward. We're going to fly over this region here. I'm going to zoom in. So you're seeing a plain over here. They call that the Tombaugh region, named for the guy that discovered Pluto. And you're seeing mountains miles tall next to that plain. And even more incredible, stratification of atmosphere on the planet. That's real imagery there. It's not a digital artifact. Pluto has a stratified atmosphere.
Takes about 30 minutes on the image to come.
From Pluto, 8 times 40 is 320 divided by 60 is, it takes about 5 hours, 5 or 6 hours.
Oh, right, that's all.
Yeah, it's way out there.
So why do they deplanetize?
That's a good question. Let me show you this image first. I want to show you all the moons of the solar system. I shouldn't say all the moons. I'm going to show you the highlighted moons of the solar system for sizes and colors and stuff so you can kind of get an idea. There's our moon over here. Can't even see Phobos and Deimos from Mars or Dactyl. Those are the 4 famous moons of Jupiter. There's Titan, the one I hope to show you guys tonight. Triton, the one with the cantaloupe surface. Pluto has a moon. Charon is the name of it. It actually has 2 moons, I believe. But that's the size of Charon. And then we get to Dysnomia, which is the moon of Eris. It's far out, man. It is way far out. Pluto is about 40 times the distance of Earth to the Sun. Eris, which is nearly the same size as Pluto, is 3 times that distance. It was discovered in 2005, along with another what they call trans-Neptunian object. Eris is a dwarf planet. By all means, we categorize this differently than a planet. It didn't make sense to call this a planet. It was too small. As it zoomed towards the sun, as it got closer to the sun, it actually passed within Neptune's orbit. When the guy discovered this, when the team discovered this, they presented this and said, we found this new thing. If you're going to call Pluto a planet, we need to call this a planet. And we need to call, on the same day they presented another dwarf planet called Makemake. They said, listen, we found these 2 things, and if Pluto's a planet, by all means, these need to be planets. And if these need to be planets, you need to be warned that there are more coming, because as we're observing our solar system, we're finding more of these objects. Most likely we're going to find dozens more, maybe hundreds of more. We don't know how many we're going to find, but what we do know is that what Pluto, if you categorize Pluto as a planet, you're going to have to add many more planets to this, the family. And to give you an idea of the orbits, here's Pluto. Pluto dips into Neptune's orbit, and so does Eris. Or at least comes close. These, what we're calling Kuiper Belt objects, they don't follow normal paths like our planets. In fact, whereas all these other planets kind of ride around in a disk shape around the sun, these other objects kind of sweep in and out of that disk, so they're clearly not planets. Anyways, the IAU, the International Astronomical Union, came out with a statement that said, there are 3 things that you have to do to be a planet. You have to go around the sun, you have to be massive enough to achieve what they call hydrostatic equilibrium, that is, you're going to become roughly spherical. And 3, you have to clear your own neighborhood in your orbit, meaning nearly all the objects are not, you're not sharing your orbit with many objects. This essentially kicked Eris out of the possibility, or out of the running of being a planet, and in 2005 it kicked Pluto out. So the world of astronomy nearly unanimously said that makes sense. Categorically, Pluto doesn't fit the description. It is now a dwarf planet. I know several astronomers that think that's hogwash, that Pluto should be grandfathered in, that it still should be considered a planet just because it's always been a planet. I think I fall on the side of it's not a planet. But maybe it's just because it hasn't, I've only been into astronomy for a decade or two. So maybe if it was a planet nearly my entire life, I'd have a hard time giving it up too. So as we venture outward, we'll see comets. These comets come from a cloud, we believe, envelops our solar system called the Oort cloud. These comets sometimes venture inward into the interior of the solar system, and we see these beautiful displays, these comet tails. This, of course, is probably the most famous comet. It was the first comet that we realized had been here before. Until we saw this comet, we weren't sure, I should say, until the gentleman, Edward Halley, recognized that this comet has been here every 75 years or so, and it keeps coming back. Until then, we didn't understand comets very well. Of course, nobody calls him Halley on this side of the world. We all call him Halley, and this is his comet. This is Halley's comet. So comets are periodic ventures into the inner solar system. We believe they originate in this Oort cloud. This is another famous one. This is the comet that really got me interested in astronomy when I was 17. The Hale-Bopp Comet made its way into our skies and hung there for several weeks, months, and amazed us all. It piqued my interest in astronomy. And not too long ago, we flew a spacecraft to a comet and landed on it. That was the Rosetta mission. In fact, just last week, I believe, we crashed the original spaceship onto the surface on purpose after we had landed a probe on the surface. Looks like a big rubber ducky. It cannot be overstated how difficult that mission is. To fly a spacecraft and meet this weird object that ventures into our solar system on this highly eccentric path, to meet it in orbit and then land something on it is just phenomenal. This is a close-up of the comet 67P. This is an image right before we landed. I use landed in quotation marks. We actually bounced on the surface of it. It was an accident. The harpoons didn't fire like we thought they would. And it bounced a couple times before coming to rest. That shadow is the shadow of the probe on its way to land.
Gravity on this?
The gravity is 1/100,000th of our planet. So like very, very little gravity. Just an amazing mission. Jaw-dropping, really. And this next image is actually a logarithmic scale of our solar system, showing the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They didn't even include Pluto. But I show this because one of our spacecraft did something really incredible too. Voyager 1 lasted way longer than we thought it would. It continued to transmit data, and I think it still continues to transmit data. But in 2012, it sent us data showing that it left the heliopause, which is a fancy way of saying it left our solar system. It encountered what we call interstellar space, and that's amazing. That is amazing that we made a robot and we sent it out into interstellar space. It's the only one out there right now that we know of. And maybe someday it will get out to a star. This is Alpha Centauri. It will take many moons, millions of years, maybe billions, before it could get to another star. Alpha Centauri looks like a hop, skip, and a jump away from the heliopause, but really, it takes, what did I say, 5 hours for light to get from the sun out to Pluto. It takes 4 years for light to get here from our nearest star to our solar system. 4 years traveling at light speed. It is an immense distance away. And a light year, by the way, is something like 6 trillion miles. So unless we find a way to break the speed limit, that is to go faster than light, I don't think we're going to be an interstellar species. But it's exciting to think about. In the meantime, we can collect light from these objects, and what we found is nearly every star has planets. Nearly every star we look at, we're able to detect either planets being forming or planets going around it. And some of them we've detected solar systems, meaning multi-planetary orbits.
Is Oort cloud also influenced by sun's gravity?
Oh, definitely. Definitely. The Oort cloud is weakly associated with the sun. And we believe that's where all these comets originate and dive inward to the solar system from. I say all these when it's actually pretty rare, but it does happen. I think it makes sense to take a moment and give you, I said I wanted to do a walk of the solar system, but I don't think we're going to do that tonight. But what I can do, and you guys can do this at home, maybe I can have a young person's help. Somebody, can I have your help? What we're going to do is, I just got some printer tape from an old school calculator. We'll go like this. All right. So take this. That's roughly your height, right? That's not your height. It's got to be your height, because this is going to be your prized possession here when we're all done. Roughly your height. Right there. And we'll clean the edges off just a little bit. What we're going to do is we're going to build a scale model of the solar system. And you guys can do this at home. You can do this with a piece of string or any long piece of paper. But it's really hard to convey the sizes and the distances involved. In fact, that's like the most challenging aspect of astronomy, is trying to wrap your mind around the distances. So is this a wall? This is a wall. What I'm going to write here with my fancy astronomy pen, I'm going to write sun. Actually, could we have the lights on? Sure. It'll be easier. And at the opposite end, we're going to write Pluto. Pluto. All right. Now what we're going to do, we'll fold this in half. And of course, at this size, you couldn't really even see the sun. The sun would be much too small on this scale to even see. Maybe you could see it. Maybe it'd be like a speck. But the planet's completely invisible. So you fold it in half. And that little fold, we're going to write Uranus. There's Uranus. Do you guys remember where Uranus is? It's a gas giant, so it's on the outer part of the solar system. So in between Uranus and Pluto, we have, see, it's test time. Time to see if you guys are paying attention. Between Uranus and Pluto, it's Neptune. There's Neptune. All right. Next planet inward from the sun. I'm sorry, inward from Uranus. Saturn. Yeah. So I just folded those sides in half. So there's Saturn. So we got, why don't you hold that so everybody can see? Stand up here. So what's your name?
Justin.
Justin? Justin's holding on to the Pluto side. And there's Neptune. And there's Uranus. And there's Saturn. And the sun's here. So next thing is, let's see. To fold that in half, what's the next planet inward? From Saturn? Jupiter. So here's Jupiter. Things are getting tight. We're heading towards the sun coming from the furthest part of the solar system. So Pluto, Neptune, Uranus, Saturn, Jupiter. Fold this in half. Fold this in half. What do we get? Asteroid Belt. Asteroids. There we go. Fold that in half. Fold that in half, and we get to Mars. Here's Mars. And how many planets do we have left? We have. Oh my gosh! I gave you guys the key to the test. I'm ashamed. We have 3. So roughly, and this is roughly, I want to say within like 5% of the way it really is. We're going to fold the remaining part into 3 equal parts, which gives us, here we go, Venus, I'm sorry, I failed the test, Earth, and then Venus, and then Mercury. Here we go. This is a solar system model that'll fit in your pocket. You guys can do this at home. But this is what it looks like. We are 93 million miles from the sun, and we are right here. That's us. 1 astronomical unit. You continue outwards, and you have to go absolutely astounding distances. Light hours. It takes light hours to get there from here. And there's Mercury, Venus, Earth, and Mars. These are the rocky planets, the interior of the solar system. And there is the rest. What's amazing is when you picture these planets going around, and you know that these planets are infinitesimally small on this scale, it gives you an appreciation for what our solar system is. That is to say, what it isn't. Our solar system is mostly empty space, desolate, with the exception for a few specks of planets.
Except for all that dark matter.
We won't even go into that. Maybe if I come back for a Big Bang talk, we can talk about that. But yeah, mostly empty space. All right, Justin, you get to go home with your very own solar system model. In the last moment, I'm going to skip ahead to one final image, and if you hit the lights one more time. Some size comparisons here. I'm not going to go over them. There's Earth. There's a great impact on Jupiter. Now this is the image I wanted to end on. This is an image from Voyager 1. Carl Sagan convinced the scientists that worked for NASA to take Voyager 1 as it was passing Saturn and on its way out of the solar system. He convinced them to turn Voyager 1 around for an image. And when he first lobbied for this idea, most scientists laughed it off. They said, it's silly. When you take a picture, he wanted to do a quote-unquote family picture of the solar system. But most of the scientists said, like, that's silly. If you do a family picture, you're not going to see anything because the sun will wash out nearly everything. All you're going to see is like a speck if you get lucky. And Sagan finally convinced everybody.
This is just a reminder that the library closes at 9. It is now 8:50.
He convinced them of extending the library's hours for astronomy presentations. He convinced them that that's exactly the point. And if we zoom in on the exposed image of the one on the left, I don't know where I set my laser pointer. The image on the left is the Earth panel. The image to the right is the Venus panel. But we're going to zoom in on the Earth panel. And it's worthwhile to read verbatim what Sagan wrote about this image. And this is how I want to conclude the night. This is from his book, A Pale Blue Dot, and if you have an opportunity, wonderful book, and you can actually listen to the whole thing read by Carl Sagan on YouTube. He says, look again at that dot. Oh, by the way, do you guys see the dot? That pale blue dot in the orange sunbeam? Look again at that dot. That's here. That's home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter, forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely indistinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Think of the rivers of blood spilled by all those generals and emperors so that in glory and triumph they could become momentary masters of a fraction of a dot. Our postures, our imagined self-importance, the delusion that we have some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in a great enveloping cosmic dark. In our obscurity in this vastness, there's no hint that help will come from elsewhere to save us from ourselves. The Earth is our only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for now, Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. This is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Thank you.